Welcome to Machine Tool Maniacs, the podcast where machining, fabrication, entrepreneurship, and bringing ideas to life collide. Around here, every story is a success story. I'm Matt, a second-generation manufacturer who's been in the shop since I was in diapers, learning the tools, the trade, and the people behind it all. Nearly everything in our daily lives is passed through a CNC machine. And we're here to spotlight the makers, turning raw material into reality. Whether you're dreaming big or building bigger, this is your inside track to making it happen. Welcome to the first live recording of Machine Tool Maniacs. I am here with Will, and today we are going to be talking about your machine's foundation. Introduce yourself, Will.
Hi guys, I'm back.
In the flesh.
Yep, this time I'm in the flesh instead of via Zoom call. So I don't know if that's better or worse for you,
It's
Matt,
great for me. I mean, as you can see, I mean, we kind of, if you're watching this podcast episode, we kind of have a bit of a mess. So it was a bit of an experience figuring all this setup out, but we're working with it. So just to reiterate, Will and I have a bit of a series going where we just kind of talk about CNC machines, and we are kind of doing a sub-series within that series where we're going to start breaking down the components just so everybody has an understanding of the construction of their machines, the electronics of their machines. We're probably going to do an episode on all the electronics. We're going to do an episode on the hardware, the ball screws and stuff like that. But this episode is going to be about your foundation. So whether that's your casting, whether your machine is made of a weldment or an epoxy granite machine, we're just going to talk about all the different types of foundations you're likely to find.
The whole idea behind it is to help give you guys as machinists and shop owners and whatnot just a little more information, maybe things to look out for, not in a negative way, but to just be mindful of when you're looking to replace or upgrade equipment, or even for specific applications. Again, we're all about educating and helping our industry grow and thrive and succeed.
Yeah, so just to start off, Will, explain to us how your foundation of your machine tool affects your accuracy, your finish, your rigidity. How does it affect it?
Well, just like with your house, you gotta start with a good foundation. Otherwise, whatever you build on top of that is not going to be a success, or it's not going to hold up well. So with your machine foundation, I like to say that if the machine has more ass to it, then we're in good shape.
Okay.
And I say that mass
junk in the trunk.
Yeah, have more junk in the trunk. That's probably a better way to say that, just so that way people, aren't like, what did he say? But in machining, two of our biggest enemies in terms of our parts is thermal instability and vibration, harmonics. And depending on the materials we're running, the kind of cutters, all these different things, they play into that. But one of the biggest ways to help mitigate both of those is to have more mass in the castings or in the foundation of the machine. Mass wins because thermally it causes you to have more thermal stability because there's more thermal mass. It takes longer for heat or cold to cause the machine to shift. And then the other thing that you end up having is the density of the material. Having more mass there, it tends to quiet down some of the vibrations and the chatter and whatnot. And I realize the design of the casting also plays into that, where it has ribs, where it doesn't have ribs. Different stuff like that also plays into vibration, but mass really is the winner. Because you brought up on the foundation, you brought up the differences where you have weldments, you have epoxy granite, you have cast iron. Actually, one that is happening a lot more over with some of the European builders is they use ultra high performance concrete.
Yeah, I've seen that. I've seen that.
And so those all have different harmonic frequencies. Like steel weldments, if you were doing just steel, like nothing else with it, it's just a steel base, that machine is going to have a harder time with vibration because steel wants to vibrate more. It's not as dense. It's strong, but it's not as dense as cast iron is. So it wants to kind of almost have a ring to it and vibrate. Same with aluminum. Don't get me wrong. I've seen aluminum tombstones that are really awesome on production machines and whatnot. That's real easy to machine and whatnot. But if you're doing anything that's harder, you're either getting real aggressive with your cutting or you're doing harder materials, an aluminum tombstone isn't going to work as well because it has too much of a tendency to want to vibrate and whatnot. So same with the machines itself. You have those different materials.
Let's back up and just kind of isolate out just cast iron first. So let's talk about the pros and cons of a cast iron machine base.
So cast iron machine base, one of the big advantages of that is it's relatively easy. Like for the last century, machines have been built out of cast iron because it's plentiful, it's durable, it's got good vibration dampening, it's easy to machine. Like some of the most accurate machines, like you know who Moore Specialty Tool is, right?
No, I don't.
So Moore Specialty Tool was a company that built machine tools. Started clear back in, I think, the 1930s, but they built jig bores and jig grinders. And if you've ever heard of a book called Foundation of Mechanical Accuracy, that was published. It was written by one of the presidents of Moore Specialty Tool, and it was published by them. And if you can find a copy, I think they still print them in batches every year, but the information in it is just phenomenal because it starts out with like with the Moore jig bores, they didn't use like a square way. They used a triangular shaped way, and they would have two of those running in parallel. It's the hardest way to build a machine like that because it's hard to make sure that you have geometric accuracy on two sets of triangle ways that are parallel to each other. But when you do have that, it's an extremely stable and an extremely rigid way of doing it. That's how a lot of older flatbed lathes were set up, where they had two V ways and then a flat way. And the apron or the carriage would ride on the two V ways and on the flat, and then the tailstock rested on one V way and the flat. And the two V ways made it so that way the carriage didn't want to cock one way or the other.
Yeah.
And so cast iron, it's inexpensive. It's been done for years. There's easy ways to machine it and to make it very accurate. Like even hand scraping is an advantage of the cast iron, because you can do that and make a very, very flat, geometrically accurate surface that way.
And how about for thermal stability? Where does cast iron stand in the echelon of machine base construction?
If you've got sufficient enough mass to it, it's phenomenal because I'm trying to remember where I learned. I think it was from a guy that I worked with when I worked for the Haas dealer, but he told me that cast iron has a thermal expansion coefficient of 67 parts per million per degree of change in Fahrenheit. So like a 10-degree shift in that is like 670 parts per million, which I think equates to, what was it? It ended up being that all things being equal, it would be about a half a tenth for every 10 degrees of temperature change or something like that. Don't quote me on it. Look it up if you really want to know. But that's just what I'm remembering.
Memorized that much.
So, but it works really well. I mean, you look at DMG Mori, Okuma, like all these guys, even on their ultra precision, high precision machines, they are still using cast iron castings. Even with when they do the linear rails and stuff, it's still on a cast iron base because it works so well and it's so easily handled. They have all the processes in place for working with it. So that's really one of the big advantages. A disadvantage of cast iron is that it's not something that just anybody can make. Like you have to have a foundry, create the molds. You have to, you send out, you have the castings made, and it could be a little while before you get them back.
Yeah.
Coming from a manufacturing side of it.
Yeah, there's a lot of process.
So there's a lot of process there. If you're designing and building a machine, if you are trying to iterate and find the optimal design for the casting, it gets a little expensive because again, you got to have new patterns made, have new castings made, machine them, do all that stuff.
Do you know how they're making those patterns for those? What the most common?
Most common is sand casting. Is the most common method for cast iron.
Okay.
And even in cast iron, there's a couple of different grades. So if I remember right, you have gray iron. Pig iron is kind of the raw material that gets used. Then you have gray iron, which is like what your Haas's and some of your more economical machines are made from. Then you have, I can't remember there's another grade of cast iron in there. I don't remember what it is. And then you have the mehanite castings. Now, mehanite isn't necessarily a specific type of cast iron. It's a process that is used during the cast. It's a process used when casting the cast iron that is supposed to make it more. It makes it more uniform and it makes a stronger cast iron. But I'm drawing a blank on what some of the specifics are to the mehanite stuff.
Got it.
But you'll see.
Yeah, I've seen that before. I'm looking at specs.
Exactly. You'll see a lot. Nodular iron. That was the other grade of iron that I was thinking of. So you have gray, you have nodular, and then you have more of the mehanite type cast iron. So sorry.
Yeah.
But yeah, you generally speaking, your better quality machines are going to be using a mehanite process when making the castings. So think of your Moris, your Okumas, your Kitamuras, stuff like that. So
very nice. So moving on, let's talk about weldments.
Mm-hmm. Weldments, where they excel are price and ease of iteration, because to do that, it's literally you just plasma out, your new metal pieces and then weld them up, and so you can iterate quickly. Steel weldments are not very good in terms of vibration dampening. Again, they want to kind of sing. Mm-hmm. They have a tendency to not be as stiff as cast iron is. They're strong, but they tend to have a little more flex to them, hence why they kind of tend to ring and vibrate a little more.
I actually was poking around on YouTube recently and I think I was watching a video, somebody did like a retrofit, and he bought some old European built machine. I don't even remember what the brand name was, something we don't hear much about here in the States. But one interesting thing that I thought about this machine, it was a weldment machine and it was filled with sand.
Mm-hmm. And that was something that I wanted to bring up with a weldment. So some of your epoxy granite machines, the way that they'll do it is epoxy granite, you're not going to have you're not going to drill that and then thread those holes after the fact to machine it.
Yeah.
It ain't happening. But the way that like the epoxy granite tombstones from AME are, and the way a lot of the epoxy granite machines are done, is that they will design weldments that have places for like steel or cast iron inserts or whatever that they'll put in place, and then they will cast those into the epoxy, into the epoxy granite. So you get the vibration dampening and the thermal stability that the epoxy granite has, but then you have the areas to be able to machine and put like your linear rails and all of your other fasteners and different things like that. And so you bring up the weldment, the steel weldment, and then it's filled with sand. That's done to help give a little more vibration dampening to the machine. And really, that's something, if I'm remembering how Hard Hinge on their super precision lathes did stuff, they had what they called Harcrete, which was the same thing. They would do like a weldment, and then they'd fill it with epoxy granite to give it more, again, thermal stability and vibration dampening.
So what are some commonly known machine tool builders that tend to use weldments? Do you know of any?
I know Haas on certain machines do weldments. So think of like your compact mill, compact lathe, the old mini mills. I don't know if they're still using a weldment on the reboot of the mini mill, but the older mini mills, they had a base that was a steel weldment, and then they attached a small cast iron base to that that they built the rest of the machine on. They have those. A lot of the newer Haas gantry mills, so like the GR series and whatnot, they have a lot of weldment pieces in them as well. You mentioned the Europeans. European builders have a tendency to use more weldments as well.
I don't quote me, but I recently heard that Grobe uses them. I'm not 100% certain on that.
Grobe does have certain parts of their 5-axis machines that are very heavy weldments.
Oh, okay.
If I remember right, they do, and then Starag has a couple of machine models in their horizontal line that the column, or a lot of the column, is heavy weldments as well.
Actually, when I went to Spain, I got the opportunity to go to Spain and go to Sorlus.
Oh, that's cool.
They were building a huge gantry mill, and the two bases that the gantry rode on, they were weldments too. So it's common.
It is, and especially when you get into bigger machines, it's like the larger.
Yeah,
the larger the
casting.
Yeah, there's not a company that builds a casting that big, or even if they could make a casting that big, you're out months and months and months to get it made. And then something that seems dumb, but it's part of it, is how long does it take for that casting to cool enough to where you can actually take it and use it and machine it?
Yeah, I mean, there's, I guess not to backtrack too much into the cast iron stuff, but there's such a thing as seasoning a casting. What do you have any comments on that?
Actually, yeah. There's a cast iron, just by its very nature, has a lot of internal stresses. I don't know if DMG Mori still does it, but I know some of the older Mori machines, like think NL, the old SLs, stuff like that, they'd get the castings in, and then they would leave them out in their casting yard for like a year just to chill out and let the casting try and let it work out a lot of the internal stresses and stuff. And in Foundations of Machine Tool Accuracy, the book from More Specialty Tool, I can't remember his first name, but the guy that wrote it, he's like, yeah, I don't know how much I believe in that whole seasoning thing. He says a lot of the challenges is that, and the reason people say that you need to season the casting is it has to do with how it was fixtured and how it was machined, inducing stresses into the casting. I genuinely think it's a little bit of both. I think that you have the stresses from the casting process and cooling and everything, and I think with proper heat treating and stuff like that, it helps reduce that. But then I also think when you start machining cast iron, because I saw this when I worked as a machinist, we had to do some cast iron parts. Our shop, they would rough in these cast iron parts, and then they take them off the machine and let them sit in a non-constrained state for a day or two, and then they put it back in the machine, measure it, and then adjust their program accordingly. So I think there's a combination of factors when you start getting into some of that stuff. Okay. Excuse me.
So next, we're going to talk about the epoxy granite casting and bases. I have personally seen these in machines like Kearns and Sharon's. I've seen
Hermela's.
Hermela's. Very high-end 5-axis machines seem to have a lot of epoxy granite type bases.
And I think a lot of that goes back to vibration dampening and thermal stability, because with those epoxy granite or mineral castings, you have the epoxy resin, the binder. You have different sizes of aggregate and different types of aggregate that are all mixed in there. And so all of those aggregates, they all have a different harmonic frequency that they would vibrate at. Same with the resin. And so because you have so many different not parts, but because there is such a variety of materials there, that there's not really one frequency or whatever that is going to cause a lot of vibration to propagate through that base. It's going to be disrupted a lot. It's kind of the same theory that RegoFix uses on their power grip system, because you have, so for the power grip stuff, the main tool holder and body of the collet is made out of one material, and then you have your collet sleeve, which is made out of a similar but a different type of material, and then you have your end mill, usually carbide, that's made out of a different material. And so you have 3 or 4 different materials in there that are helping to minimize the amount of vibration that propagates. And then the epoxy resin, and because you've got so many different types of material in there as well, it doesn't expand and contract all the same way as like having a monolithic cast iron base does.
So is this generally just about the same material as your surface plates, your granite surface plates?
Yeah, it ends up, it's a very similar construction. I know, I'm pretty sure Zeiss, on some of their like shop grade CMMs, instead of using a piece of natural granite, they will do the mineral casting, and they have a process for machining it and getting it flat and square and whatnot. But they do that because it's easier to make it in the size that they need, and they get better performance overall out of it.
Okay.
And so that's why you see a lot of those high-end machines being able to do it, because like a Hermela or a Chiron or whatever, they might be doing stuff like a turbocharger impellers or whatever, or blades and blisks for aircraft engines. And so they're going to be running at higher speeds, and they're going to be running for an extended period of time to machine that. And so they need to have that stability to make a consistent part throughout. So that's generally why they use that. And it's easier for them to make that, instead of having to wait on a big casting house or whatever to make some of their parts.
How about any lathes? Have you ever seen epoxy granite foundations?
Oh yeah, the hard inch super precision. There's another company, and I'm trying to remember. I think, was it Emco? No, it was. There's a European builder that'll also use for some of their high precision lathes, that they'll use an epoxy granite. Maybe like Spinner? Casting.
Is that ringing a bell?
Pardon?
Spinner?
Possibly Spinner. I think that might be where I was thinking, was the Spinner. But it's not used as much on lathes as it is on mills, or gantry type systems or whatever.
Really noticed. I've always noticed when they're on the 5-axis mills. That's really where they seem to show up.
I wonder if the reason that they don't use them a lot on lathes is because once you start trying to hold, sub half thou tolerances on a lathe, that at that point in time, you're almost better off to go with a cylindrical grinder to try and hit those tighter tolerances than that. So that might be why, because I've seen cylinder grinders and surface grinders and stuff that have epoxy granite bases.
Got it.
So,
Well, then the last one we wanted to talk about was concrete and polymer concrete bases.
yep.
What do you have to say about those? You kind of already brought them up.
I actually think it's a really cool concept.
I think so too.
There aren't a lot of builders that are using it that I've seen, but I think there's more that are starting to play with it. And it's kind of because it has some similar advantages of the epoxy granite, but with less expense. They are ridiculously heavy machines, but it's also usually used on really big machines that you want that weight there. You know, great big turning centers, great big machines. And so I'm interested to see where it goes, how that affects our industry.
Yeah, I know I got pretty excited about recently just about little garage mills and little hobbyist level mills, and Langmuir builds that little MR1.
Which is a sweet little
Yeah,
machine
for your
for
garage.
your
And the concept behind that is it comes as a kit, and it's sheet metal, and there's obviously the uprights and stuff are all made out of tube steel and some cast iron, but the concept behind it is that after you get it set up, you fill it with concrete, and that's what gives it its weight and its structure.
Yep.
So it makes shipping cheaper. It makes, it takes some of that cost that they would have to pass on to the consumer, and it mitigates a lot of that cost. And so in my mind, I'm like, oh, this is a really cool concept, right? Get it to the customer, then have the customer make it heavy on site, like by filling it with concrete. So
Yep, exactly.
so even on a little hobbyist scale, I just think that's a really cool use and concept.
Oh, I agree. I've been toying with the idea of doing a couple of little, self CNC builds, like a CNC router and things. And I've totally gone down that rabbit hole of, okay, so what kind of concrete can I use to make the base of this instead of having to try and come up with some kind of a weldment or whatever. So
yeah. So on to the next section where we're going to talk about why weight is important. So why is weight the cheat code for machine accuracy?
I know I keep harping on it, but it's really vibration dampening and thermal stability, especially thermal. I'm just going to put this out there. I know I'm going to sound like a Haas hater, and I'm not meaning to. I'm just acknowledging the fact of what it is. The UMC series of machines, especially the first generation or the original style of UMC 750, it's a great little starter 5-axis machine. But you want to talk about a thermally unstable machine. I've seen guys, I've seen this with my own testing and trying to dial in like centers of rotation and whatnot to really make it to where my customers can run it. I have seen where running the machine and then letting it sit for even a half hour, 40 minutes, so think of a lunch break.
Yeah.
I've seen it to where it will have 1 thou to 1.5 thou variation just because of that half hour of downtime. And so a lot of my customers that are trying to do really precise parts on them, I tell them you start it up in the morning and you get it running, and then if you're going to stop and go to lunch or something like that, you have a program that is running that machine at similar feed rates and spindle speeds as to what your main program does, and you just have it run that. Just so that way it doesn't cool off and change, because you will chase your tail all day long trying to follow the thermal changes in that machine.
Yeah. And not to just pick on Haas, because there's a lot of machine tool builders that build machines on the lighter end of the spectrum. And I feel like everybody wants to look at performance, right? What's the torque? What's the horsepower? What's the rapid speed? What's the tool change, chip to chip time? But I feel like not enough effort is put into considering the machine's mass, because the machine's mass It impacts your surface finish.
Yep.
It impacts your ability to hold tolerances throughout the day. It impacts your tool life. It impacts your machine's accuracy.
Oh, yeah.
So what good is your machine if it's fast, if it can't do anything you need it to do quickly?
Well,
right?
and even
if you're chasing it around all day long,
Yep.
doesn't matter if it's fast.
Well, and even again, going back to what we were saying is, going back to the Haas, it's like, okay, let's say, you have a DMU 50, right? So that's what, like a 40 horsepower spindle, 20,000 RPM spindle or something like that is an option. Okay, you take that spindle and motor combo from the DMU 50 and you mount it into a Haas. How much torque are you applying to those structural elements of the machine?
Yeah.
It's like, it could be fast, it could be it could be whatever, but you start applying that much actual power to your piece that you're cutting or whatever, and you're going to start having castings and structure that are going to want to twist and tweak a little bit, and that throws you out of tolerance. So great example. You can find a video that shows the Haas UMC, the castings and everything. Compare that to, like, say, a DMU, a DMU 50 or DMU 65 monoblock, right? Mm-hmm. I watched a video on that the other day, and completely different casting designs. And part of it is because the DMU, they're also trying to take into account the thermal growth. But one of the things I liked is the whole Y-axis bridge moves, or the whole X-axis bridge moves in the Y-axis. It's not just a column that's coming out like the Haas. And the reason is because they want to keep the length or the distance from the center line of the spindle to that casting. They want to keep it consistent so it has a consistent rigidity. Whereas on the Haas, if you're machining something closer to the back of the machine, that's going to be a more rigid spot than if you're out closer to the operator door, because you start getting that cantilever effect.
Yeah.
And so if you've got that cantilever effect and then you're really trying to hog on something, even on the Haas, it's going to want to start, even with their spindle horsepower and stuff, it's going to want to tweak and cause that deflection. And so, yeah, the mass and rigidity are really big, and the weight, and some of the way you get the rigidity is to have thicker, heavier castings.
Yeah, and I think you're referring specifically to the Evo. Is that
The Evo.
The Evo it's like the way they have
the way they set that up.
It's pretty cool.
I looked at that and I went, oh, that's sweet.
Yeah, it's pretty smart. That's for sure.
But that also brings up, like, the Okuma, the Genos. Like, when I was selling machines, that Genos M560 was a bugger to have to compete head to head with, because Okuma had the price point down to where it was really competitive, but it's a double column machine. Yeah. Like, its kinematic structure, it is rigid. It's like a 15,000 pound machine for a 40 by 20. Yeah, it might even be more. That might be closer to
18.
Yeah. And I mean, it is a solid machine.
Yeah.
And you get the symmetry of support because it's the double column design, and like the head, it's only moving in the X and Z, and then the table moves under the column. You lose a little bit of height clearance for taller parts.
You lose a little bit of Z, X, and Y on that machine.
You lose just a little bit, but man, can you just get after parts with it. Mm-hmm. It's a great, solid performer.
Yeah.
I know I'm going to sound like I'm advertising machines or whatever, but I'm acknowledging what I see. Like, great example, the Takumi H10. It is a double column machine. It was designed to compete against the Makino F5.
Okay.
Which is also a double column 40 by 20 machine. And those, again, they're awesome. That style, that small double column, makes for a really rigid, really good performing machine for thermal stability. Then you start throwing on, you can throw a 50 horsepower spindle in there, and you can have it be 20,000 RPM, and you're not going to have the deflection. You're not going to have things moving. You're not going to have the twist like you would even in a normal C-frame machine.
Yeah.
And then because now you've got more thermal stability, it's easier to either control or account for it as you're running like a long run program.
Yeah.
Quick pit stop. If you're enjoying the show, hit subscribe and drop a rating. It helps more machinists and makers find us. Tell a friend. Tell your crew. Tell the guy running the second shift. Follow me along on social media at machine_tool_maniac for thoughts, updates, and some funny memes. We're growing this community with more guests, more value, and more stories that push people to create. So if you've got a niche product getting manufactured or a shop with a cool story, email me at machinetoolmaniac@gmail.com or check out the website machinetoolmaniac.com for merch. All right, back to the episode.
So how about leveling? Tell us about leveling a little bit, because I think those terms get thrown around a lot, and a lot of us don't really know. I mean, even, including myself. You hear like, oh, 3-point base leveling or this and that. So tell us about leveling.
Okay, so this is where it gets a little interesting. Well, not interesting. I don't quite know the word to describe it.
If you're interested, it's interesting.
There's a little more nuance when it comes to some of this stuff. Leveling the machine, okay? So most guys think, okay, we set it on the ground, we put the level on the table, get the bubble in between the lines, and we're good. Mm-hmm. But in reality, to level a machine is just the beginning, right? So, for example, on a Haas, you set your level up and you get your side-to-side level good. And you make sure your level's calibrated, because like my level, it rides around in my truck, and it's not the bumping and hopping around that causes the problem. It's the thermal changes. I have found that I can, in the springtime, if I get stable temperatures, I can calibrate my level, and I'm good to go from one machine to another, and we're good. But the minute it starts getting into the fall and it starts cooling off, I have to calibrate my level almost every time I use it, because just the temperature changes the internal components just enough that's like, okay, I got to tweak this to get it good, right? So you start off by leveling the machine, and level is just that. It's earth level. But then once you've got it leveled, now you've got to work on making sure your geometry is good, because there is that flex in the castings and whatnot. And so once the level is done, you put it away. You level it, and then you set it up so you can run your table from front to back on the y-axis in the case of the Haas C-frame, and you can see if there's any twist in the y-axis. And so then you make your adjustments to your screws so you get the twist out. And even if the machine were sitting on a 45-degree angle, so it's not level per se, as long as all of the base and the column and the table and the head are square to each other, and you don't have any twist in the y-axis, it'll still make a good part.
Yeah.
Even though the machine is sitting on a 45 degree.
So it can be square to itself.
It can be square to itself, and that's really what you want, is to be square to yourself. We talk about the machine foundation, but what's that machine foundation sitting on? So like for a Haas VF3, it's like a 14,000 pound machine, something like that.
Okay.
So that can sit on a truly 6-inch thick slab of concrete, and you're fine. Once you start getting up into heavier machines, once you start breaking into that 25,000 pounds on the machine, then your 6-inch slab starts to be slightly inadequate. Compare that to, say, something like a Kitamura Mitrunion 5G 5-axis machine. That's like a 30,000 pound machine almost.
Wow.
It's a boxway 5-axis. They guarantee like 1 micron accuracy through full travel, right? They are beasts.
I didn't realize they were that heavy.
Technically, that machine is classified as a simultaneous 5-axis jig boring machine, not just a machining center. So they can hold crazy tolerances. But in order to hit those kind of tolerances and accuracies, Kitamura requires that you have a foundation, a concrete foundation under it. Well, that concrete is going to end up being almost 4 feet thick. And I forget what the exact, length and width of it is, but it ends up being like 8 or 10 yards of concrete that you're putting in there.
Isolated pad.
And having it isolated and stuff.
With steel. Yep. Yeah.
But that's what allows that machine to have enough thermal stability and to be, and actually you'll have bolts that go down into the concrete where that's anchored, and it holds, and it comes up through the leveling feet of the machine, and then the machine is anchored to it. So essentially that big ass concrete block becomes part of the structure and foundation of the machine itself.
Yeah, and I think that's a good point you bring up, and it's probably almost every machine tool builder specs out to achieve the accuracies that a lot of them advertise. Somewhere in that proposal, in that paperwork, in those manuals for that machine, they are going to establish some sort of specification for a machine foundation, and rarely is it a 6-inch slab of concrete.
Yes.
It's almost always an isolated pad, at least 24 inches thick.
Yep.
So you may be seeing like, oh, we guarantee accuracies up to, whatever, but you got to read the fine print of what they're saying you have to do to get those accuracies.
And that's something that I found when I was selling Kitamuras and quoting them, is everybody was looking at the marketing material going, oh yeah, 1 micron accuracy, this is amazing. And it's like, well, that is an amazing number. But then when I start talking to them, they're like, so is this, we should be able to do that here. And it's like, no guys, back the train up here. You want to hit that kind of accuracy? That's great. We can do it. But here's what you're going to have to provide in order to make that happen. And me and our buddy Nick have had several conversations on this. And that is, it's like, once you start needing to consistently hit tolerances sub a half a thou, it's not like the whole manual goes out the window. It's your approach your approach to regular machining goes out the window, because now you have to be worried about temperature, humidity, foundation. Yes. We were talking about that Kitamura 5G 5-axis machine. And it's like, okay, guys, to do that, you have to have this foundation, right? But then you're going to have to build a room inside of your shop that this machine lives in, and that it has its own environmental controls for that room. And then we can even go so far as you physically, as much as possible, you actually physically disconnect the electrical cabinet from the machine. And so what you do is, it's not like you're pulling it away or whatever, but you'll disconnect the bolts that hold it to the machine. So it's technically only tethered by the wires from the electrical cabinet to the machine. And the reason is because if you're truly trying to hit those tolerances, just the temperature from the electronics in the cabinet will induce heat enough into the casting to cause that to not hit those tolerances. It'll cause some thermal growth movement in the machine.
Jeez.
So once you start wanting to hit half thou and under consistently, it's a totally different animal than your regular job shop, plus or minus 2 or plus or minus 5 kind of work.
So there you go.
Sorry, that was a little bit of a digression, but it does tie in.
Things that folks got to consider, especially when they're trying to hold tight tolerances. And with the world that we find ourselves moving increasingly into, engineers just keep tightening the noose on those tolerances. And, even in my lifetime, it seems like, I remember once upon a time, plus or minus 15 thou was the norm. Mm-hmm. And now, a lot of times you go into places and their sheet tolerances is plus or minus 2 thou. Mm-hmm.
I think some of that is because these young buck engineers have got to, they got to prove themselves. Whereas the old guys are like, Yeah, that's not critical for fit, function, or form or whatever. So if that's 15 thou, whatever, I don't care. And they would only call out certain features that were critical
Yes.
to have tight tolerances.
So let's discuss.
Sorry, one other thing. You hear about 3-point level.
Oh,
That just makes it fast to set up. I mean, you got to have a pretty stiff casting to be able to level the machine and have it hold geometry, like a Makino horizontal A51NX. It only sits on 3 feet. So to hold their tolerances that they do and only sit on the 3 feet is pretty amazing. Like, it's a solid casting. The problem you run into is, and it's not a matter of if, it's a matter of when that machine gets crashed, what do you have to do to be able to bring it back into tolerance? And so, great example, Kitamura horizontal, right? You can technically level that machine on 3 feet and get it leveled, but it's got 10 feet under it. And they guarantee that to be a 1 micron machine. And talking with their service guys, they're like, yeah, if it crashes, it's a boxway machine. So, we don't have an easy way to shim things to bring it back into spec. But what we can do is we can tweak this foot here just a little bit, and we can tweak this foot here just a little bit, and bring it deliberately twist the casting in a specific place to be able to bring it back into spec.
Oh, okay, so that's interesting.
Yeah. So we talked about that DMU 65 Evo. That sits on 3 feet.
Yeah, I think that's one of DMG Mori's big claims. They always like to brag on their 3-point leveling.
But they're like Makino that way, is that they have designed the casting to be stiff enough that not only can you level it on 3 feet, but it can live and cut good parts on 3 feet, and you don't have the deflection. But that's part of why you pay what you pay for a DMG Mori versus some other machines.
Well, that makes good sense. What you say, so you're right. If you twist a casting that's true to itself, good luck getting it untwisted.
Yeah. What do you have to do to bring the geometry back into spec?
Built into it based on the leveling on the pad. So I can definitely see positives and negatives for both situations.
Me too.
So speaking on, we've been talking a lot about configurations. We're going to go ahead and start off by talking about configurations, casting configurations, so to speak, for milling machines.
Yep.
So the most common is going to be your C-frame casting. So explain to us what a C-frame casting is.
So the easiest way is the reason it's called a C-frame is because when you look at the casting or the machine without the sheet metal on it, and you look at it from the side, it looks like the letter C. Yeah. You've got the base casting as the lower leg coming in. You've got your column as the vertical part of the C. And then you've got a casting that comes out and holds the head. And usually that comes out to about halfway or just past the halfway point of what the y-axis travel of the machine is.
Yeah.
So if you've got, say, a Haas with like a Haas VF9 or something with 40 inches in Y, the center line of that spindle needs to be about 20 to 21 inches out from the column and out from what the furthest back travel of the table is, which it's an inexpensive design to implement, but it's also not the most stable because you've got so much hanging out here that when you have to start really drilling and putting a lot of force out on that very end, it kind of causes, kind of like when you over tighten a C clamp and it splays out just a little bit. Same kind of thing will happen on a machine. And so again, it's an inexpensive design to build. Every company builds a C-frame machine or has built a C-frame machine at one time or another. But once it's an economical design. Doesn't really offer you much advantage in terms of performance. We talked about kind of a double column bridge style machine, so like the Makino, the Takumi, the Genos, or the Okuma stuff. Like that's what we looked at, and that offers you more stability because you have 2 columns coming up and supporting it, and you're changing the way that the head moves in relation to everything else. So it's a very stiff design. So it's a little more expensive to build, obviously, because you have more material, another column. It's also a little more expensive because it takes a little more to get the geometry in and have it be correct, right? So that's kind of where you end up with the double column style. Then you end up, you can jump from there, and when you start getting into bigger machines, you get what's called a gantry design, where instead of the table moving in an axis, the whole bridge, like the head column or the head, the y-axis, everything moves across the table, right? But those are usually designed to be more for high-speed type machining. And for very large parts. I mean, I would, if you have, your column and your bridge and your head and everything, that's a consistent weight that you can account for your servo tuning and everything else, and you can have a large envelope rather than having to account for, a big part sitting on a table and then having to move the table and the part underneath the column, underneath the bridge. So some great examples of like gantry style machines, DMS for their routers, 5-axis, especially for doing like composites, some aluminum and whatnot. A lot of times they're set up that way, where it's a bridge and the whole bridge moves up and down.
You know what? One easy way that I like to think of it is typically on a C-frame. So I guess to back up even a little further, we're almost exclusively talking about vertical mills at this point.
Yes.
On a C-frame machine, your X and Y are almost always on the table. And then on a double column machine, typically you'll have your Z and either your X or your Y above and another axis below. So typically on a double column machine, your X and Y axis will be broken up between the head and the table. And then gantry machines, all three, your X, Y, and Z, are on the spindle.
Thank you. That's a great way of clarifying the differences. My brain started just information dumping there without
everything
clarifying.
You said was valid, but I guess if somebody's walking up to a machine, that's a good way you can typically kind of delineate the basic structure that machine has. So how about horizontals? It's almost all horizontals are pretty much the same configuration, aren't they?
They have there's some slight differences, but like horizontal machining centers are essentially all the same, for lack of a better descriptor. You'll have like the old Mori NH series, they're box in box, driven from center of gravity design. And you'll have, say dual y-axis ball screws and dual z-axis ball screws, which is awesome. I think that was one of their best designs, honestly. But you'll have that. But essentially, there's two main designs of horizontal machining centers. You'll have one where the column moves. The column has the spindle in it, and it will move up and down in Y and left and right in X. And then you'll have your pallet will be what moves in Z, and that moves closer and further away to the spindle. Right? Then you have, and this is generally for bigger horizontals, but there were some smaller ones that were designed this way, where the pallet or the table, or like where a pallet will sit basically fixed, and then the whole column moves in and out for Z, up and down in Y, and then it can also move left and right. So like think Haas HS series of horizontals. And then there's a slight variation on that where it still moves up and down in Y, and that column will move in and out in Z, but then your table moves left to right. So, I guess there's a couple of different configurations that way, but horizontals, there's not a lot of different designs. For a horizontal 5-axis, you have those designs. Grobe is about the only, and DMG Mori has a couple where the spindle moves in and out in Z. I don't know. I don't know how to describe that, because the Grobe, that's such a unique 5-axis, because the table moves up and down in Y, and it rotates and swivels, or it tilts and swivels, and then the head moves in and out in Z in this big long package that it reaches out with, and then it also moves in and out, so or side to side. Sorry. Now that I've said stuff and I'm starting to think through all the different machines, it's like, okay, well, there's this one, and then there's this one, and then there's this one.
There's all kinds of flavors.
Yeah.
Let's move on to lathes.
Yep.
So starting with flatbed lathes, which is your classic style lathe. That's kind of where they all started.
Yep. Flatbed CNC lathes. Generally, they're either for a tool room setup, like think Haas tool room lathe, or Clausing makes a really good one. Ganesh, they bring in, or Expand Machinery, excuse me. They bring some in from Taiwan that are pretty solid, but that's usually more for onesie twosie kind of work, tool room work, or very large parts. Think oil field work, like 10-inch, 15-inch through bore, threading pipes and shafts and things like that. Mm-hmm. That's generally where they do really well, is that kind of work. And it's a very stable design, relatively easy and inexpensive to manufacture. Probably, maybe, no, never mind. I was going to say something, but now that I think about it, it would probably be incorrect information.
Okay.
So you've got that. Then you have two different flavors of slant beds. Okay, so
first explain to us what a slant bed is.
So a slant bed is where your x-axis, instead of being flat and basically parallel to earth level, it's slanted. Usually it's 30, 35, or 45 degrees.
Yes.
Depending on the builder. Those are the three main angles for a slant bed. A shallower slant, so like say a 30-degree slant, gives you an advantage of, you can usually, especially on like a y-axis live tool lathe, you can have a larger swing diameter or a larger diameter part that you can still access with those live tools and whatnot. When you go to a steeper, or the disadvantage of that 30-degree slant is it makes the machine deeper, so it's got a bigger footprint, right? Mm-hmm. But then you can go to a 45-degree slant bed, which geometrically speaking makes it a little easier to produce, makes it easier for going, okay, well, if I move down 1 thou this way, it's just, 45, 45, 90 triangle, so you know that you're going to move, if you move down an X 1 thou, then it's going to change your point by about 1 thou or whatever. Mm-hmm. Makes sense. But the advantage that gives you is that it makes the machine a little shallower, so it can fit into a smaller footprint, but it also eats up some of your swing capacity that you can get in there. So when looking at your turning centers, your slant bed turning centers, you definitely want to go, okay, what truly is the largest part that I think I'm going to be bringing in consistently, and then help that, or have that help you in making your decision on the machine. So slant beds, you can have what's called a true slant bed versus a not a true slant bed. A true slant bed is that the casting is actually slanted. If you were to look at it from the end, you'd have your 90-degree on the back of the machine in relation to the bottom of it, where it hits where it touches the concrete, and then all whether it's linear guides or boxway, those are all tilted on a 45.
Yes.
That's a true slant bed. That is going to be your strongest and most stable design out of a slant bed, because it's all integrated. Compare that to something more like, I'll use the Haas SL series because that's the one I can think of off the top of my head, where the Z-axis linear guides are actually flat and parallel to the ground, and then it has a casting that sits on top of it that's called the wedge, and the wedge is what gives you the slant for your X-axis. That's easier to machine and easier to make geometrically correct, but it's also a weaker design, or weaker maybe isn't the term I want to use. It's not as rigid of a design.
Well, another thing I've also noticed, so another big example of that I have is the big difference between when you're talking about the Akuma Genos lathe.
Yes.
And the Akuma LB series
Yep.
lathe. LB series are true slant bed castings.
Yep.
The Genos lathes is like you described. It's a flat casting that's actually based on the old Cadets that have been around.
Oh wow, that's a name I
years.
haven't heard in a while.
Yeah,
the Cadet.
you go into so many old shops and those things are still chugging along.
Oh yeah, you can't kill them with a 10-pound hammer.
But one thing I notice when you're going from a Genos lathe to an LB is because of that wedge design, and because you have basically what is essentially an angle plate.
Yes.
Right? The second you try to add a y-axis to a machine like that, they limit out on travel a lot quicker, because you have an angle plate stacked on another angle plate that's stacked on a flatbed casting.
Yep.
So you have a lot of stacking going on there.
And that also makes it to where it's a lot harder to make it to where your tool moves in a true 90 degrees to the x-axis.
Yeah.
Like you like on a true slant bed lathe, you can literally have it to where there's one wedge, or I've seen some machines where they actually put they have a casting that will move the turret in a true 90 degree movement.
Oh, right.
In relation to the x-axis.
Compound.
Yeah, there's not too many that do that, but there are machines out there like that. And then you bring up the compound, so you'll have a wedge. So on a true slant bed, you will have a casting that will kick up, and then in order to create the x-axis or the y-axis movement, you have to synchronize two movements to make it move in that way. And like you said, you run out of stroke really quickly with it.
Yeah.
And you can't be up at like at the very top or at the very bottom of travel. You have to be somewhere in the middle in order to make that work.
Yes.
That way.
And then the last format I wanted to talk about was vertical lathes.
Oh yeah, VTLs. I'm starting to see more and more VTLs showing up here in Utah, which is good, because really they are, I will say, in a way, they are an unsung hero of machining.
Yeah.
They are for large diameter, short length parts.
Mm-hmm.
Because you notice, like on your regular horizontal turning centers, if you want to have a large diameter, you usually end up having a really long base or a really long bed. And it's a really expensive machine when you do that. Even if your part, say you want to turn a part that's 28 inches in diameter, but it's only like 8 or 10 inches deep. It's like I'll use Haas as an example. The only Haas machine that you're going to have that you're going to be able to do that on is like an ST40 or an ST45. And the shortest ST45 is able to do like 60 inches between centers. So you're not using all of this length and whatever, and it's taking up a really big footprint.
Yeah.
Now compare that to like a 900 or a 1000 millimeter VTL, right? The footprint is like the size of a Haas VF2, so it's a small footprint. It's a little taller, but you can do like a 30-inch diameter part on those usually.
Yeah, and Akuma has those. Mazak.
Yep.
DN has vertical lathes.
Yep.
I'm pretty sure.
DMC, Leadwell. Let's see, who else are there? Then you start getting into some of the other Taiwanese builders, like UG has some, Yamasaki. They all have, even Mighty Viper has
Shibura
VTLs.
Do
Shibura, I don't know if they do VTLs or if they just do really big mills. Shibara, also some people might know them as Toshiba machine tools.
Yeah.
They might have some VTLs, but those ones might be really big VTLs. Yeah. So anyway.
Well, cool. Let's give out some practical takeaways from this segment that we're doing. If you're looking at buying a machine or Maybe you're looking at taking on a job and you have machines already sitting on your floor and you're trying to decide, hey, can this machine even make this part? Or what can I expect out of my machine's performance? What do you think?
Yeah, first and foremost, if you're looking at new machines, looking at upgrading equipment, don't just focus on like rapid speeds and chip to chip time and stuff like that. Like look at stuff like machine weight. Look at the actual design of the machine. If they'll show you pictures of what the castings and stuff look like.
Yes.
Like really look at that stuff to see, okay, is this going to be a real rigid machine? And I know people are not nearly as they are not as fascinated by that stuff as I am. I'm a little touched in the head when it comes to that stuff.
Touched in the head, huh?
Yeah. That's a Theo Vaughnism that I picked up as touched in the head. But you know, that is still something to consider. Because yeah, rapids can help, but really how much time does your machine spend doing rapid moves? It spends more time in feed rates. So you're better off if even if your rapids aren't high, you know, or super fast, if you can run a faster programmed feed rate and the machine will actually hit those numbers, that's going to end up making more chips. That's going to end up making more money.
I agree.
So
So yeah, look at the materials.
Yep.
Look at how the casting's built.
Yep.
Or the foundation, if it's not a casting, if it's a weldment. Look
Yep.
at how that's built. You know, make sure you're considering what you're trying to make.
Yep.
Right? It's not all about, can I fit the size of part I'm trying to make in my workspace, but can it actually take the types of cuts that you want to take?
Am I going to be machining, 80% of my stuff is aluminum, or am I focusing more on cutting Inconels and Hastelloys and, high carbon content steel, like where there's going to be a lot more torque and a lot more needed stability for taking those cuts.
Yeah. Well,
So
I think this is all very good information. I hope anybody just looking at their machines, can start thinking about some of this stuff. You have any other takeaways from this episode?
Yeah, honestly, if your machine isn't cutting as well as you think it should, don't automatically assume don't automatically assume that there's something wrong with it. It could just be that the machine is settled and it's out of level, or your geometry needs tweaking, or something like that might be a little easier to diagnose and to go, okay, here we go. And if you don't know, if you're not sure what's going on, don't be afraid to call somebody and talk to them and, ask some questions. At the end of the day, I know most of the guys I deal with in the industry, we're more than happy to share whatever knowledge and insight and understanding that we have, trying to help people out.
Yeah, well, thank you for joining this first live episode of Machine Tool Maniacs podcast. And the next episode, we are going to start talking about your machine's mechanical components. So ball screws, linear and box guideways, things like that. So tune in next time for the Machine Talks sub-series that we have going, where we'll be talking about the next level of your machine's build components. Any last words?
No, not really. Don't have anything else I need to say.
All right. Well, thank you for joining Machine Tool Maniacs.
Thanks, guys. Have a good one.